Hi, I'm Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know about lab skills and how they apply to the Regents. The first thing you're probably saying is, why are you wearing safety goggles? Well, you shouldn't be asking that. You should know why I'm wearing safety goggles. I'm wearing safety goggles because I'm in a lab. The Regents loves to ask questions about safety. And they say questions like, what are the correct safety precautions you should take when doing this experiment? And the correct safety precautions are almost always, you could always say, wear goggles or wear an apron. Now they got a little tricky, the Regents. They got a little smart, and they said, wait a minute, everyone keeps giving us safety goggle answers. So one of the questions said, instead of safety goggles and an apron, list another type of safety precaution you could take when in a laboratory. And it's still very simple. Anything that makes common sense is a safety procedure. Girls, tie your hair back. Don't wear loose jewelry. Don't wear open-toed sandals. Anything that makes sense that would be dangerous in a lab, don't do it. And list that as a safety precaution. Another thing they sometimes ask about is mixing acid and water. When you want to add an acid in water, if you want to dilute an acid, for example, you actually have to add the acid to the water. Because if you added the water to the acid, when the water hit the acid, it may splash up and spill on you. So you always want to add the acid to the water. Next thing you need to talk about is percent error. Now, percent error is quite easy because it's right on reference table T. Percent error represents how wrong you were in the lab. There's a set answer for certain things, but then maybe you found something to be a little different. That's your error. For example, let's say you get a problem like this. A student determines the density of zinc to be 7.56 grams per milliliter. If the accepted density is 7.14 grams per milliliter, what is the percent error? Well, the measured value, the value the student found in the lab, was 7.56. The actual is 7.14. How do we do that problem? We go to table T, we do 7.56, which is the measured value, minus 7.14, which is the accepted value, over 7.14, the accepted value, times 100. And then you do your math, you get 0.427 divided by 7.14, and you get 5.88%, or 5.9%. That means that student was 5.9% wrong, because that's the student's percent error. Okay. The next thing we need to talk about are independent and dependent variables. A lot of students have a lot of problems with independent and dependent variables because it does get confusing, and because a lot of the times the teacher doesn't ask those questions in class because they take for granted that the student knows it. But we at Regents Tutor want to make sure that you know everything you need to know for the Regents, so we're going to teach you independent and dependent variable. And really what you'd have to do is pick out the independent and dependent variable. The independent variable is the variable that you as a researcher or you as a lab student can change. The dependent variable is the variable that is dependent, the one that depends on the independent variable. Let's say you want to see if temperature affects the rate of a reaction. You're going to change the temperature. You may put some reaction at 40 degrees, some at 50 degrees Celsius, some at 60. You're changing the temperature. What is dependent on that change in temperature? The rate of a reaction. Therefore, the rate of the reaction is the dependent variable, and the temperature is the independent variable. And sometimes you just have to pick them out of an experiment. Sometimes they also ask, where on the graph is the independent and dependent variable represented? The independent variable is generally on the y-axis, and the dependent variable is generally on the x-axis. The next thing we need to talk about is unit conversions. Unit conversions is like when we want to go from milliliters to liters. Now, you don't have to do a lot of that on the Regents, but there are some questions where the Regent says they give you a molarity problem. And if you don't remember what molarity is, check the molarity concept. They give you a molarity question, and they say, okay, the molarity, you know, is grams per liter. So they say you have this many grams and this many, the molarity is moles per liter. So you have this many moles and this many milliliters. You then have to say, wait a minute, we want liters, we have to convert milliliters into liters. Now there are two ways to do it. The first way is to come over here to Table C and Table D. Table C is too confusing. So we're not going to go over Table C except to tell you that there is Table C if you need to use it, but it also shows you the symbols. Kilo is K, deci is D, centi is C, milli is M, and so on. So if you're talking about milli, well, you're talking about milliliters. Well, now, Table D shows the selected units. So liters is L, and that measures volume. So no, there are those two tables that tell you the units, the symbols, and what they represent. Moles represents the amount, joules represents energy. Become familiar with Table D. Table D is important because it gets you to think about what these substances are. But let's say they want to convert milliliters into liters. Because again, they gave you milliliters. Let's say they gave you 1,000 milliliters. And you want to convert that for a molarity problem into liters. Regents Tutor has a different trick. And the trick is a mnemonic device. It takes a little bit longer, but it actually makes more sense and it's more fun. And the mnemonic device is King Henry died, Mother or Larry or Grandma, and we'll talk about that in a sec, didn't care much. And you're probably saying to yourself, what does that mean? King Henry died, Mother, Larry, Grandma didn't care much? I'll tell you what that means. First of all, let's start with this box. This is the most important part. Because this represents what units you're in. If you're in meters, it's Mother didn't care much. If you're in liters, it's Larry didn't care much. If you're in grams, it's Grandma didn't care much. And you can make up your own for any of the different symbols that are listed on Table D. And the way you do this is you basically take the ones you need to worry about for the Regents' purposes are kilo, obviously the units, deci, centi, and milli. So you want to go from milliliters to liters. So you want to know 1,000 milliliters equals how many liters. What you do is you go to milliliters, which is right here. You find out where you want to go to liters. So you want to go one space over, two spaces over, and we want liters three spaces over. That's going from milliliters to liters. And if you move three places to the left, you do the same thing here. Where's the decimal point on 1,000 milliliters? The decimal point is at the end because it's a regular number. You move three spaces to the left, 1, 2, 3, and you get 1 liter. That works for any kind of problem. If you still have questions on Table C or you want to go over this further, come to the chat and we can talk about it. But this is the extent to which you need to know how to convert units on the Regents. So just remember the mnemonic device. King Henry died. Mother, Larry, or Grandma didn't care much. And that's a good way to think of it. The next thing we need to talk about is the thing that gets kids crazy. But it's not going to get you crazy because I'm going to teach you a great trick. Significant figures. Ooh, I could see you already sweating. Significant figures is actually a little bit easier than it sounds, but it's a little confusing, but you're going to get through it, I promise. Significant figures tells you how many units you know for certain. If you have, let's say you have a reading 1.782. That has 4 significant figures, and we're going to go over the rules in a second. And again, remember, all this is on your Regents Tutor review sheet to go over, but we're going to go over it right now. This tells you, when you get a number like this in significant figures, you know to certain that it's 1.78. But you're not sure a little bit after because maybe your instrument of measurement wasn't as accurate. You don't know if it's 1.783, 1.781. You know it's a little more than 1.78, and you're estimating this digit. So anytime you get an equation or you get a number, you know that the last digit is actually an estimate. And you know certain to the digit before that. That's the purpose of significant figures. That doesn't help you figure out how many there are. But now I'm going to help you figure out how many there are. There are rules that we talk about with significant figures. For example, like every whole number is significant. Any zero between two whole numbers is significant. Any zero after a whole number or non-zero digit after a decimal point is significant. I'm not going to even worry about those rules. I'm going to teach you a great trick. And it just involves you knowing a little bit of geography. It's called the Atlantic-Pacific rule. You can see on the screen that you have a map of the United States. On one side you have the Atlantic Ocean, and on one side you have the Pacific Ocean. And the rules are, if you know that, you know it all. The Atlantic and Pacific rule goes like this. If a decimal point is present, P, present, you start from the left, the Pacific side. If a decimal point is present, you start from the Pacific side. You then go to the first non-zero digit, that digit plus every other digit on is significant. So let's say we have the number 0.020. Is there a decimal point present? Yes, there is. Start from the Pacific side, which is the left. Go to the first non-zero digit. So not this one, not this one. Oh, here we go. First non-zero digit. That number and everything else after that is significant. So how many significant figures does this number have? 2. That's significant figures. The other thing you have to know about is the Atlantic rule. And the Atlantic rule is just the same, except the other side. If a decimal point is absent, go to the first non-zero digit, except you start from the Atlantic side, which is the right side of the map. Go to the, well, it's actually to my left, your right, whatever, it doesn't really matter. You just know it's the Atlantic side. So if there's a decimal point absent, you start from the Atlantic side, go to the first non-zero digit, and everything else is significant. Let's say we have the number 1030. Decimal point present? I don't see one. Do you? No. Start from the Atlantic side, go to the first non-zero digit. Everything else is significant. 1, 2, 3. We know there are 3 significant figures here. And that's how you determine how many significant figures there are in a certain problem. The next thing with significant figures you have to know are the rules for multiplication and division and addition and subtraction. And the rules for multiplication and division is that the answer to a significant figure problem will always be the same number of significant figures as the number with the least number of significant figures. For example, let's say you have, well, you can see it on the screen. Let's say you have the numbers 2.00 times 1.750. Well, we know based on the rules, start from the Pacific side, there's decimal point present, and you know that there are 3 significant figures in 2.00 and 4 significant figures in 1.750. Your answer has to have the same number of significant figures as the number with the least number. So since one number has 3, the other number has 4, we want only 3 significant figures. So the answer is 3.5, but we have to put another significant figure. It's 3.50. So it has 3 significant figures. The rule for addition and subtraction deals with how many digits there are after the decimal point. The rule is, for addition and subtraction, whichever number has the least number of digits after the decimal point, that's how many significant figures your answer has. So let's say you have 1.28 plus 3.5. 1.28 plus 3.5. Well, you know your answer is only going to have 1 digit after the decimal point. We don't worry about before, we just worry about after the decimal point. So we add it up, 8, 7, 4.78. Is that our answer? No, because we need to have only 1 digit after. It's 7/8, so we have to round it to 8. And the answer is 4.8. And that's how you do addition and subtraction dealing with significant figures. And I'm going to actually teach you one more significant figure problem and how it relates to density. So first let's talk about density. Density represents the mass over volume. Do you need to remember that? You probably know it already, but you don't. It's on table T. Density equals mass over volume. So let's give you a problem with density with significant figures. What if they said a sample of aluminum has a mass of 12.50 and a volume of 4.8 milliliters? What is the density expressed to the correct number of significant figures? Well, density equals mass over volume. 12.5 divided by 4.8 is 2.717. But in 12.50, there are 4 significant figures. In 4.8, there are 2 significant figures. In a division and multiplication problem, your answer must have the same significant figures as the number with the least number of significant figures. You need to have 2 significant figures. Your answer then is 2.7. One word of advice. If a question on the regions does not say what's the answer to correct number of significant figures, that means they're going to give you the answer no matter what. They're going to give you credit no matter what significant figures you put. The only time you have to worry about significant figures is when they say, place your answer to the correct number of significant figures. I hope that clears it up. Next thing you need to know about is graphing. I'm not going to spend too much time on graphing because you've done graphing your whole, probably student age. But you do have to know some things about graphing. The first thing you have to know about is how to scale an axis. And when you're scaling an axis, you have to make sure that every unit goes up by the same amount. That's the major thing you have to worry about. Every unit goes up by the same amount. You can't have 0 and then 2 going up by 2 and then start going up by 4s. So 0, 2, 6, 10, that's wrong because the first one went up by 2 and then it started going up by 4. Every unit, as you can see on the slide, has to go up by the same amount. Another thing they ask you to do on the regions is label the proper axis. And you just label it. It's very simple. They give you the information, you label the axis. And we could see some problems on graphs later on when you go to the questions. Also, sometimes they ask about filling in data tables. Same deal. They'll give you the data. Sometimes they'll ask you to take the data off of table S. And if you don't remember what table S, go to it and figure it out. It just lists all the different properties of certain substances. And that's filling in data tables, and that's graphing. And the last thing we're going to talk about in the lab is separation of mixtures. There are 3 methods of separating mixtures you need to know about. The first one is filtration. Filtration, you have to understand how a filtration works. Filtration works by having this piece of filter paper, really, with very, 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 very tiny little holes in it. And what can go through filter? A solution can go through. So if you have a homogeneous solution or homogeneous mixture, that cannot be separated by a filtration because that's going to go right through. But let's say you have a piece of water, but then something that's not dissolved in it. Like let's say you have sand and water. Sand doesn't dissolve in water. Salt does. You could not separate a mixture of salt and water through filtration because you could not separate an aqueous solution. But if you put sand in water, sand doesn't dissolve, so when you pour the water into the filter, the water is going to drip through and the sand is going to stay on top. Sometimes the regents can say, show me the setup of a filtration to separate a mixture of sand, salt, and water. Well, if you have just sand and salt, what you need to do is you need to take the sand and salt, put it in the water. What's going to dissolve? The salt will dissolve in the water, and the sand won't. Then you pour it into the filter paper. It filters through, the solution filters through, so the salt water will come through, and the sand will stay on top. And that's how you separate them. You could separate heterogeneous mixtures, but not homogeneous mixtures or solutions. How do you know if you could separate a mixture? You go on table F. If table F shows solubility, then that means it's soluble, which means you cannot separate it. If it's not soluble, that means it's not dissolved in, like sand or other insoluble substances, then you can separate it. Very important. The next thing is distillation. Well, what if we want to separate a homogeneous mixture? Distillation is the process by separating substances based on their different boiling points. So each substance has their own unique boiling point. And you can find that on table S, certain boiling points of elements, but different boiling points of different substances depending on what they are. Let's say you have a saltwater solution, and you want to get the salt out, or the water out, excuse me. You have to distill it. You have to heat it up. You have to boil it out. What's going to happen is boiling point of water is 100 degrees Celsius. The boiling point of NaCl is a lot higher. So the water is going to evaporate, or it's going to distill out. It's going to vaporize pretty much, and you're going to be left with only the salt. So the way to separate with distillation is to heat it up to evaporate whatever you want out, but you have to remember with distillation there are different boiling points. And the last thing you need to know about is chromatography. And chromatography is just a way to separate mixtures. And the way we separate certain mixtures is we take chromatography paper. And let's say we have a beaker of water. What happens is, we have this beaker of water, we dip the chromatography paper in, and let's say you want to separate ink. You put a little piece of the ink on, and what happens is, different parts of the ink stick to the chromatography paper in different ways. Some stick harder, some don't attract as much, and what happens is the water starts to go up the chromatography paper, and it literally carries the different parts of the ink up with it. So some may stop over here, and then another color may stop over here, and so on. And you're separating it using chromatography paper. And that's another way to separate mixtures. So you need to know the 3 ways to separate mixtures: filtration, distillation, and chromatography. Now I hope you learned a lot about lab skills. There's not that much information you need to know about this, but all of it is really important, and they ask about it on the Regents. So make sure you go over all the questions that relate to lab skills after you do this lesson. And don't only go over the questions that you don't know, go over the questions that you do know, and listen to all the video explanations for both, because that's when you're going to get the most out of it. And if there's anything you're still not clear about, come to the chat, look over the review sheet. Whatever you need to do, we'll be here for you at Regents Tutor. Make sure you learn the material. Hope you learned something.